This wheel weighs over a ton. It is traveling at 70 miles per hour. It is sitting on a rail that is only 70 millimeters wide. There is nothing locking it in place. No bolts, no clamps, no magnets. And yet, in the entire history of modern rail, a properly maintained locomotive wheel has never, not once, simply rolled off a track on its own. The reason why defies everything your brain tells you should be true. It is not what is holding the wheel on the track, it is the shape. A single steel wheel, tipping the scales at over a ton, barrels down the track at 70 miles an hour. All that mass, all that speed, and yet the only thing touching the rail is a patch barely the size of your thumbnail, about 1 square centimeter. The rail itself is just 70 millimeters wide. There is nothing wrapping around it, nothing gripping from below. Steel on steel, with a friction coefficient as low as 0.1, sometimes a little higher, maybe 0.35 if conditions are perfect. For comparison, a car tire on asphalt gets nearly double that grip, up to 0.8. It is like trying to balance a refrigerator on a butter knife and expecting it to stay put, even as it rockets forward. Your instincts scream that this setup should be a recipe for disaster. By every rule of common sense, these wheels should slip, skid, or simply topple off at the first bump or curve. It looks impossible. So what is the invisible force at work? Why does this system not fail? The answer is not in magnets or clamps or any secret locking device. It is something far subtler and far more ingenious. In the early 1800s, even the engineers did not buy it. John Blenkinsop, working at the Middleton Colliery in 1812, refused to trust smooth wheels on smooth rails. His solution was a rack and pinion system, with teeth on the rail and gears on the locomotive, because everyone assumed friction alone could not possibly move a heavy train uphill. The idea of relying on simple contact between iron and iron seemed reckless. By 1825, George Stephenson took a gamble with the Stockton and Darlington Railway, running iron wheels on iron rails with no mechanical grip at all. The train not only moved, it hauled hundreds of tons of coal in its first week, showing that adhesion, just weight and friction, could work. But doubts lingered. Some inventors tried leather-covered wheels, hoping for extra grip, only to watch the leather burn and shred under the strain. The real test came in 1829 at the Rainhill trials. Stephenson's rocket, running on bare steel, outperformed every rival. The competitors with racks, gears, or leather treads fell away. The answer was not in a clamp, a gear, or a trick. Geometry itself would solve the impossible. The secret is hidden in the profile of the wheel, a shape so subtle you would miss it standing right beside the track. Every locomotive wheel is machined as a shallow cone, not a perfect cylinder. The taper is precise. For every 20 millimeters across the tread, the diameter changes by just 1 millimeter. This 1:20 ratio is the quiet genius behind the system. The two wheels are locked together on a rigid axle, so they always rotate at exactly the same speed. But when the wheel set shifts sideways, even by just 5 millimeters, the wheel on one side rides higher up its cone, while the other drops lower. Suddenly, the rolling diameter on one side is 0.5 millimeter larger than the other. That means the outside wheel travels a slightly longer path with each turn, nudging the axle back toward the center. The train corrects its own path through pure geometry, encoded into the shape of the wheel itself. This self-steering action works up to astonishing speeds, only reaching its dynamic limit known as hunting at about 200 kilometers per hour. No electronics, no sensors, just the physics of a cone on the rail. The conical wheel works its magic in silence, but every locomotive hides a backup plan, a steel lip called the flange. This ridge, jutting 28 to 35 millimeters below the tread, is the last line of defense when geometry alone cannot keep things in check. On straight track, the flange barely comes close to the rail, but on sharp curves, rough joints, or if the wheel set drifts too far sideways, the flange steps in, catching the railhead and stopping the wheel from wandering off the edge. It is not designed to guide the train day in and day out. It is there for emergencies, ready to intervene when the system is pushed past its limits. Over time, every flange wears down by 0.2 to 0.5 millimeters for every 100,000 kilometers traveled. If half its original height is lost, usually around 14 to 17 millimeters, the wheel is pulled from service. That margin is not just a number, it is the difference between a reliable backup and a silent risk. Maintenance crews watch these measurements like hawks, because when the flange is gone, so is the failsafe. A train rounding a curve faces a new kind of challenge. Centrifugal force tries to fling it outward, while the rails must keep it balanced. The solution isn't brute strength or hidden clamps, it's the careful tilt of the track itself. Engineers call this Cant, or superelevation. The outer rail is raised, sometimes by as much as 180 millimeters, to match the sideways push of a speeding train. On a typical main line, a train traveling at 70 miles per hour on a 1,000-meter radius curve sits perfectly balanced with about 130 millimeters of cant. The math is precise. Too little tilt and the wheels press hard against the outer rail. Too much, and the load shifts inwards. This geometric balance lets the conical wheels do their work, keeping the train steady and the flanges out of play. The track's tilt and the wheel's shape act together, quietly solving what seems impossible at first glance. Every fraction of a millimeter matters. Maintenance crews rely on axle lathes to restore the wheel's exact conical profile, a process called reprofiling, usually from 100,000 to 300,000 kilometers. But geometry alone isn't enough. Hidden cracks can spell disaster. Ultrasonic testing scans for flaws as small as 2 millimeters. If a crack escapes detection, the result can be catastrophic. In 1998, a fractured wheel tire on an intercity express in Eschede, Germany, went unnoticed. The wheel failed at high speed, derailing the train and causing over 100 deaths. Precision maintenance isn't just routine. It's the final guardrail against the impossible. Every journey relies on a shape, not a lock or a code, just geometry guiding steel at 70 miles per hour. The impossible is solved, quietly, by a curve you will never see.